Welcome to the video on normal probability distribution function. In this video, I'm going to explain the concepts related to normal PDF. And as we build in the next video, I'm going to apply these concepts to solving a problem. So let's start. So before we start analyzing the graph that is given, I would like to present a situation in statistics and probability which can lead into the formation or observation of such a pattern. So let's take the case of a sugar packaging company. It does a packaging in standard sizes that are expected to be, let's say, 1 kg. Yeah. So if I say the mean of all the sugar bags that are produced in the factory, let's say if it is expected to be 1 kg. And before that, it is important to say, let's say the sample size is very huge. Let's say it makes 10,000 sugar bags in a day. Yeah. So we are analyzing the stats and probability on a per day basis, for example. Yeah, it's a very high number. So one clue is that PDF is applicable for a very high sample size. Yeah, and those values of the variable can be in a very high range from lower to higher. So let's also consider the expected size of the bag is 1 kg, but there is, because of multiple reasons, there could be variation in the packaging, and those reasons could be due to automation, could be due to packaging defect, could be machinery, could be manual error. But let's assume that everything is not perfect, and there will always be some defect, although very low in number. So let's say in our case, sigma, the standard deviation, is found to be 0.1 kg. So these are the inputs we have. And let's see, could there be a distribution for the probability, which we represent on the y-axis? Also important to mention that on the x-axis, we see the weight of the bags. Yeah, on the x-axis, it is representing the weight of the bag, and that weight will be measured in kg. Now, if we analyze the, let's say, probability of occurrence for a particular weight of the bag, then let's take some assumptions. For example, if I start from this point, mu equals to 1 kg. Let's say I take the assumption most of the bags that are packaged in the company, they are found to have the mean value of 1 kg. Maybe I can call this point as A. Yeah. So point A represents the probability of occurrence of the mean, which is 1 kg. Now, if I move to mu plus sigma, so this will be 1.1 kg. Let's also assume the probability for observing the bag to be of 1.1 kg is represented by point B. Okay. If we have a observation such that the probability of having the bag of 0.9 kg, let's say if it is represented by B. Okay. So if we have a scenario that the probability of having a bag size of 0.9 kg happens to be the same as the probability of having the bag size of 1.1 kg, then we have a kind of symmetry on the left hand and the right hand side, yeah, with same equal probabilities. Further, if we extend the logic, mu plus 2 sigma can be represented as 1.2 kg. Let's assume that probability of having that size of the bag is represented by the point C. And if it is found from the observation that mu minus 2 sigma, which is 0.8 kg, also has the same probability represented, let's say, by the point C. Yeah? And going by the same logic, if I extend, let's say if it is found in this packaging company that the size of 1.3 kg has a probability of D, which is matching exactly with the point D over here for a sample of bag size 0.7 kg. Yeah. If we have a distribution like this, so we can similarly draw infinite number of points, but the most important point you would have already observed by now that this shape in which for a particular mean value that is a highest probability of occurrence followed by symmetrical values on either side for the samples which have a size which are equally spaced with respect to sigma. Yeah. So such a shape, if I can call it as a bell-shaped curve, is known as the normal distribution. Let's see some of the properties of normal PDF. The first and foremost property is that the mean of the sample data has the maximum probability. So deliberately in this graph on the x-axis, I have not put any values, and you should be able to make out based on the graph where is the mean. So given the graph on the y-axis, we have the probability. So the point of maximum probability is, let's say, point A. So all you need to do is drop a perpendicular, and wherever it meets the x-axis will be the point of the mean. So at this point is representing the mean of the sample data. By the way, is there any way that we can indeed verify that this point, this position mu represents the mean of the sample data? So yes, there it is. So if you go towards the right-hand side, the sample data has some values on the right-hand side, and we have as many values on the left-hand side. And what we see on the graph is the probability of the x values on the right-hand side is equal to the probability of the values on the left-hand side. Also, the x values on the right-hand side match to the x values on the left-hand side. Whenever we have sample data organized in such a way, that indeed confirms that mu represents the mean of the entire sample data. Another characteristic of the normal PDF is that if I go on the right-hand side and let's say I take the point mu plus sigma, and if I draw a perpendicular, if I call this point as B, so the probability represented by the point B will be the same if I go towards the left-hand side. So equal distant point on the left hand side will be mu minus sigma. And again, if I drop a perpendicular onto the curve, the point will be B, and the probability at point B for x value mu minus sigma will be equal to the probability for the point B at a distance of mu plus sigma. So one thing clearly, B probability at B is lower than the probability at A. So all the probabilities while going down the curve will be lower than the probability at the mean position. And another point is that the probability values which for the x points equidistant on the x-axis from the mean will always have the same probability. Now, another important point is that the area under the curve and over the x-axis is representing 100% of the probability. Okay, so which means probability of x values being lower than positive infinity and higher than negative infinity is 100% or 1, which is as good as saying that probability for x in the entire range will be 100% or 1. Now, this particular point of 100% is applicable for any probability distribution function. Picture shows that the area shown in green represents 68% of the area. So what is the area in green? So this is our curve, which is known as the normal curve or the bell curve. So this is my normal curve. So if I see the area under the curve above the x-axis and between the two lines, x is equal to mu minus sigma and x is equal to mu plus sigma, then the total area will be 68%, which also essentially means that the respective area, since the graph is symmetrical, left-hand side portion will be 34% and the right-hand side portion will also be 34%. So these are the numbers which you need to remember by heart for easy reference. And you can interpret the picture in many different ways. If the right-hand portion represents 34% of the area, then this point on the x-axis has to be x equal to mu plus sigma. Yeah, or I can even say other way around. If I draw a perpendicular from the point x is equal to mu plus sigma, then it will cut the normal curve at a point in such a way that, if I can give some names, let me call it as A, B, C, and D. So if you draw a perpendicular from x equal to mu plus sigma, it will cut the normal curve at the point B such that the area A, B, C, D, A will be 34%. In terms of the probability of occurrence of the x values such that x is less than or equal to mu plus sigma and greater than or equal to mu minus sigma will be 68%. Now this picture shows that the area shown in green is 95%. So essentially the area bounded by A, B, C, D, E, and then back to A. So basically it's the area under the normal curve, above the x-axis, and between the two vertical lines, x is equal to mu minus 2 sigma and x is equal to mu plus 2 sigma. So basically, the probability of having the x values between plus or minus 2 sigma deviation with respect to the mean is 95%. Yeah. Now, if we take our reference with respect to the 3 standard deviations, so let's say we take the area A, B, C, D, E, A, which essentially represents area under the normal curve above the x-axis, and the straight lines x is equal to mu plus 3 sigma and x is equal to mu minus 3 sigma. So area in green, it represents 99.7%. In terms of probability, the probability of having x values in the interval mu plus 3 sigma to mu minus 3 sigma will be 99.7%. So in the earlier case, we have seen the area with a reference of 1 standard deviation and then followed by 2 standard deviations, and now we are doing 3 standard deviation. So as you see, 3 standard deviations are good enough to represent a good picture about the data. So it covers almost all the data. So that's the reason we normally don't analyze the probability distribution for values beyond 3 standard deviations on either side. It's time now to have a consolidated look at the percentage of the individual areas with respect to each standard deviation. So let's first focus on the green area. So as we already know, the total green area is 68%. Therefore, the area on each side will be 34%, and that is what I have shown over here. So one should be pretty clear about these percentages. A quick recollection will help you solve the problem faster. Now, focusing on the area in the pink. So that's between 1 sigma and 2 sigma on either side. So that will be 95 minus 68, which is 27%. And if we divide 27% by 2, we'll get 13.5% on both the sides. So this is what I have represented over here, 13.5% on left and right hand side. And corresponding to the area in orange, that will be 99.7 minus 95 over 2, and it will be 4.7 over 2, and which will give 2.35% on left and right. And now coming to the area shown in the yellow, that will be 100, which is the total area under the curve, minus 99.7. So this will be 0.3%. If we divide it by 2, we will get 0.15% on both the sides. So you can do your own checks and balances. For example, if you combine everything on the right hand side, the area under the curve, you should get as 50%, and same on the left hand side. So it is always good. I would encourage you to remember these numbers, since you don't have to look into your data sheet to derive these numbers during the examination. I think you should remember on top of your mind. So far, we have gone through normal PDF, and let's spend some time to understand what's a standard normal PDF. So I'll give you the scenario a bit later, in which scenarios we need to evaluate or study standard normal PDF. But for now, let me take the reference of a normal PDF. So we are very familiar now with the graph, and we know that on the x-axis we have the values with the points such as mu, and then successive addition of sigma, those points on the right hand side, and similarly successive subtraction of sigma on the left hand side. What if I tell you that due to some reason I want to have the scale on the horizontal axis changed with respect to I would like to see only the integers on the horizontal axis. Integers like, say for example, mean should be represented with 0, and mu plus sigma should become 1, mu plus 2 sigma should become 2, mu plus 3 sigma should become 3, and similarly the values on the left hand side should be -1, -2, and -3. Regarding the application of it, as I mentioned, I will come back to it, but for now I need to introduce a variable which is known as z-score. Yeah. So z-score, or simply the z value, or z, if I write a expression, z value is corresponding to x value minus the mean mu over sigma. If I introduce such a variable, so let's see what will be the value of z for different values of x. So x and z. So let's say x equals to mu. So the value of z will be mu minus mu over sigma, which is going to be 0, which matches with what I have shown over here. And similarly, if x is mu plus sigma, then what will be the value of z? It will be mu plus sigma minus mu over sigma. So mu and minus mu will cancel. This will be sigma over sigma, which is equal to 1, which is matching with what I have represented over here. Similarly, you can take any value. Maybe I'll take mu minus sigma as one value on the left hand side. In this case, z will change to mu minus sigma minus mu over sigma. So mu and minus mu will cancel. This will be minus sigma over sigma, which is equal to -1, and which is matching over here. Similarly, you can verify on your own the values 2, 3, and then -2 and -3. Now let's go into the need for having such a translation from x to z value. So before I go to the next slide, remember that a standard normal PDF is same as the normal PDF with respect to the y-axis. There is only a change in the horizontal axis. In case of normal distribution, we have x values, which is representing mu plus or minus sigma. And in case of standard normal distribution on the horizontal axis, we have the integers 0, 1, 2, 3, and -1, -2, -3 taking over the respective values for the x variables. So x equals to mu will change to z equal to 0, and x equals to mu plus sigma will change to 1, and likewise. Now, as I mentioned, coming to the specific scenario where we may be required to study the standard normal PDF, let's take the scenario wherein we have two data sets containing the weight in kg of students in the class. Data set 1 is students of year 11, and data set 2 is students of year 12. It is given that the mean of year 11 students is 50 kg and the standard deviation is 0.1 kg. And for year 12 students, the mean is 55 kg and the standard deviation is 0.2 kg. It is also given that we have two students. One student from year 11 is found to have a weight of 50.1 kg, and other student from year 12 is found to have a weight of 55.3 kg. So the question is, which of the student weighs more in relation to the fellow classmates? So this is a classic scenario where we are required to compare with respect to the normal distribution. And we know that the only common scale which can be used is the z-score scale. So let's use the z-score given by z equals to x minus mu over sigma. So if we calculate the z value for the first student in year 11, the weight is 50.1 minus mu 50 over sigma, which is 0.1. So we will get a value of 0.1 over 0.1, which is 1. So maybe I can call it as Z1. So Z1 represents the Z-score or Z value for the student who is found to have a weight of 50.1 kg in year 11. Similarly, let's see Z2. That's the Z-score of a student in year 12 with a weight of 55.3 kg. So that will again be x minus mu. So 55.3 minus mu, which is 55 over sigma, which is 0.2. This will be equal to 0.3 over 0.2. If you multiply by 10 on in the numerator and denominator, we'll get it as 3 over 2, which is same as 1.5. Now, if we try to understand with respect to the graph, in the graph, let's say the normal curve is representing year 11. Okay, so the weight of the student 50.1 has a z value of z1 is 1, so which is this value, yeah, which is same as this value. So the student's probability is represented by the point A, and we know that it is one standard deviation away from the mean of the data set 1. Similarly, if we plot one more graph, normal curve, which is for year 12, and try to locate where do we get on that graph z value 1.5. So this is z value 2 and 1.5 value will be over here. So if this is 1.5, that means between the two, this will be 1.5, and that means we will have the probability over here, which is represented by point A dash. How the student of year 12 is performing with respect to the mean in the respective class. If you see, 1.5 is further away from the mean as compared to a weight of 1 in year 11. Yeah. So with this, we conclude that student 2 weighs more in relation to the fellow classmates as compared to the student 1 in his or her own class. Important to mention here that I should have drawn one more curve and the second curve should have been for year 12. But as long as we understand the concept, that should be fine.